Okay, we are very happy to have a lecture by Konrad Deka from the Jagiellonian University of Cracow. And the title is The Relation of Topological Conjugacy of Cantor Minimal Systems is Not Borel. Please.
Okay. Thank you very much for the invitation. It's a great pleasure to give a talk here. And the title is really a result that I want to advertise here, but I will start slowly because the motivation for I want to talk today about the theory of Borel reducibility of equivalence relations. And let me first give you a motivation. So there is a number of theorems in mathematics that follow the following informal pattern, namely A, B are in some equivalence relation. If and only if some function of A is equal to some function of B. So let me give you an example. So for example, let's say A is n by n Hermitian matrix. Let's say that lambda of A is the tuple of eigenvalues in, let's say, ascending order. Then two matrices RB, AB are conjugate via unitary. By this I mean there exists U such that UAU star equals D, if and only if they have the same sets of eigenvalues. So this is just linear algebra. Or to give an example from dynamical systems, there is the following theorem. Let's say P equals P1 up to Pn is a set of is a tuple of real numbers. Sum of Pi equals 1. Pi is greater than 0 for all I. Then the Bernoulli scheme Bs of P is the following the following measurable dynamical system, where we take the set 0, 1 to n minus 1 to power z. We take the measure mu of p to z. Mu of p is the measure we have one random variable that has this distribution that it gives the number I with probability pi, and then we take infinitely many independent such random variables, and this gives a probability measure on this set, and we take them up sigma, where sigma of sigma. Okay, I'm just going to write n to z for this set, where this is the shift map. So it takes a sequence and maps it to the same sequence, but shifted one space to the left. And then there is a theorem of Ornstein that says Bs of P and Bs of Q are isomorphic if and only if their entropy is equal. And entropy of P is just sum of minus pi log pi. Okay, so okay, this is just a pattern that appears quite often, and if we have a situation like this, we say that this function of this value is an invariant for this relation. So I would say entropy is an invariant for the isomorphisms of Bernoulli schemes, or the set of eigenvalues is an invariant for this relation of being conjugate by a unitary. So
Konrad, could you please try writing a bit larger letters so that online
okay. Okay. So so obviously this cannot be done with just any equivalence relation. So let me give you the following example. Let's see B let's see be the set of 0, 1 sequences, and let's say that 2xy in C we will define the following relation E0. Two elements are in relation E0 if and only if there exists n such that they are equal on positions larger than n0. So someone could ask, is there an invariant for this? And well, we could ask, for example, does there exist a function, let's call it h, from C to R, such that x, such that for all xy in C, x is in relation if and only if h of x equals hy. And well, there exists such function for the simple reason that this is a set of cardinality continuum. So once we divide by the equivalence classes, we have actually continuum many equivalence classes because each equivalence class is countable, and we can just do, well, we could just find such a map. So it's possible, but obviously this is not really what we are looking for. We are looking for something productive in this manner, and so there should be a better way to formalize this question. Well, one thing that we can do is say, well, let's say this is Cantor set, so it comes with some topology, and we can ask, does there exist a Borel function from C to R, and again with the same property, and now it turns out that there is no such function. Okay, if we believe every nice and productive function is Borel, which you can believe or not, but it's I think we learn in I don't know, introduction to measure theory that most nice functions are Borel, most nice functions are measurable, and so on. So okay, so you could say it's a convincing argument that there is no such theorem of this kind waiting to be discovered here.
Can you say something about how you prove that there is no such Borel function?
Yes. On this set we have a measure. So on C, take well, this kind of measure that comes from flipping a coin and taking
normal countermeasure.
Sorry?
Like the normal typical countermeasure.
Yeah.
Just gives half and half on the same.
Then we have Kolmogorov 0, 1 law. So any okay, okay. Let me write this down. If A in C measurable and if X is in A and X is 0, Y, then Y in A, then let's call this measure mu, then mu of A is 0 or 1. And if you know this lemma, then the proof goes as follows. Suppose such H exists, then well, H minus 1 of let me replace this by 0, 1 just for simplicity, because you can just take an injection from R to 0, 1. So I look at these two sets, and I learn that precisely one has measure 1, the other has measure 0. So I focus on the set that has measure 1. Let's say and so on and so on. And this way I get a descending sequence of intervals.
So it is constant.
Yeah, so then I take intersection and it's constant on a set of measure 1, but that's a contradiction because each equivalence class is countable. Okay. So
So this gives kind of negative answer in a strong sense, right? That you assume that such Borel function exists, and you obtain that in fact on measure 1 it should be actually constant.
yes, it is. Yeah. We actually just used that the function is measurable. So
Another language of making is ergodic, then partition of orbits is not measurable. The same with other.
yes.
This ergodicity is not ergodicity. Because immediately you have these partitions which are not measurable.
Mhm. Okay. So in so
But in this case, the relation is not dynamical. I'm not sure you can use here. Because this is the tail relation.
That's right.
Or it's not dynamical because the
So the question is, can you prove
Yeah,
the
that's
same
right. That's
statement
right.
using the ergodic theorem? And then the question is, what is the dynamic?
Shift.
Shift, but the relation is not related to the
Relation is
shift.
different.
It's the tail relation.
Yeah.
Not
So-
okay.
Formally, you have decayed in 1.
Okay.
Yeah. Why do you use shift? You can use another method.
So I'm asking, how do you prove it dynamically? I don't see it.
Just odometer.
Odometer and what's the relation to the odometer?
So this is orbital consolidation.
oh, yeah. You treat it like +1 into orbic numbers.
Yeah. Because
Okay. So, okay, anyway. So
Okay.
what I told was not right. Maybe.
Yeah, but it's also an idea. Okay. So in larger generality, this kind of stuff has been studied by descriptive set theorists, and they have introduced the following definition. Well, let's say x, y are Polish spaces, and this means completely metrizable and separable. So this just means, most of the time it just means that we have a complete metric space that is separable, but we really care about the topology, not the specific metric. And there is the following definition. Let EF be equivalence relations on XY. We say that E is reducible to F, written E less or equal E F, if there exists and only if f of x1 is in relation f with f of x2. So this is a transitive relation between equivalence relations on some Polish spaces, and there has been okay, in descriptive set theory is a reasonably large subject. So they have written okay, there are a few books about this topic. So okay, so what we did was we're basically looking for invariance is the same as showing that something is reducible to identity, for example, on real numbers.
Borel.
Sorry?
Borel.
Yeah, Borel. Okay, and okay, there are two main sources for. Obviously, there are lots of equivalence relations. I don't need to convince you, but anytime we will be concerned with two classes of examples. G acts on X, and to be precise, okay, we will want G Polish group acts on some X, which is Polish space. And by this I mean there is some action which is Borel as a map from here to here. Then it induces the orbit equivalence relation, meaning two elements of X are such, well, the orbit equivalence relation is simply two elements are in relation if there exists G such that Gx1 equals x2. And more importantly, whenever we have isomorphism of some class of objects, so let me explain. Well, if we have some class of mathematical objects, for example, let's say countable graphs, then it's clear well, isomorphism is something that's well, it's an equivalence relation except there's no clear underlying set. And there is usually a way to get around this. So for example, let's say countable graphs. Well, this is not really a set, but we can view as a graph with in E, then Ji is in E. So so let's say graphs is a subset of 2 to n times n. Well, that have this property, and so we can now we can put a topology on this because, well, it's again just go to topology. Okay. So
I have a nice example of isomorphic class in holomorphic dynamics, rational functions, and homography is equivalence relation. Change of coordinates on the sphere with homography. And we take factor space, and it is interesting in the boundary somehow. I say about this because we just were just at the conference with several talks on this.
About the moduli spaces.
It's very special.
Examples.
Rational maps clear because you have coefficients in the numerator and coefficients of the polynomial in the denominator. But sometimes two polynomials can be skrócone according to
concept.
concept. And then becomes interesting. But it's a little bit different phenomenon. Nevertheless, it shows that. Okay, I don't want to go deeper in it.
Okay. Okay. So anyway, my point is, if we have isomorphism of some class of objects, it usually can be studied from this perspective.
So it is not only homography, but also cancellation. From pairs of polynomials.
Okay, Mr. Constance.
Hmm?
Pity I missed the conference.
Yeah.
So okay, just to finish up this introduction, they are well, the descriptive set theories, when they have an equivalence relation, they usually want to answer some questions. So so let E be equivalence relation on X. So the basic questions that we can ask is E Borel as a subset of X times X? Is E reducible? Okay, I always mean a Borel reducible to some Polish group. Okay. To some Polish group action. And by this I mean an equivalence relation of the form E gy as defined here. So the reason they care about being an S-infinity group action is because, well, here I took countable graphs, and an isomorphism of countable graphs in this context, well, it's a permutation of n, which moves edges of one graph to the edges of the other graph. So this equivalence relation is induced by an action of S-infinity, and essentially you can repeat the same pattern. You can take any other first order countable structures. For example, we could do countable groups, and we could do a similar thing, or countable linear orders, and so on and so on. So I could
Just to clarify, by permutation, you mean all possible projections or just arbitrary?
all possible projections. So okay, and so these are like three large classes of equivalence relations, and just to put a diagram, let's say these are Borel, these are S-infinity, and these are Polish Polish group actions, S-infinity group actions, and actually let me call this equivalence relation E S-infinity, because it has the property that it is the maximal among all S-infinity actions. And in this set of Polish group actions, there is also a maximal one, and I'm just going to write I don't know, E-Polish for this. This can be described, for example, as the relation of homomorphism between compact metric spaces, but we will not use this. So
Mark, this E S-infinity, it's for action of S-infinity on natural numbers?
S-infinity, we can treat it as a group.
Yep.
And the group can act on any Polish space.
But what is E S-infinity? Is it for action on natural numbers? Or
yes. So this is well, this is the relation on graphs of two graphs being isomorphic.
I see.
Okay. So all of this has been applied to study some classes of objects that come from dynamical systems.
But wait, maximality is that if I take any relation there, I can reduce it to the maximal,
Yes.
because the maximal is the most complex.
Yes.
But what about uniqueness? Does this also, let's say, can there be another maximal?
Well, okay.
I got lost. Where is the maximal?
This relation E as infinity is maximal in this class of S-infinity group actions.
Because if we have reduction, you haven't discussed let's say that we have two relations, the one reduces to the other reduces to the.
So
So
what does that imply? Does that
well, then we treat them as if they are the same from the point of view.
So this is
then, okay, so
divided by equivalence classes of the equivalence given by connecting two of those comparison relations.
yeah, well, is it not? There is a lot.
If I'm sorry, I think I said equivalence too many times, but I think that's what you said. So if we have this comparison relation, and we take comparison relation in one direction and the other direction, and we have two equivalence relations that are compared both this way and this way, we treat them as one.
Yes, yes.
So we can divide the equivalence relation, but by the equivalence relation given by this. I love this sentence, by the way.
Yes.
Okay, thank you.
And then, yes, then we would have a partially ordered set, and I'm just basically drawing some partially ordered set.
Okay. It makes some beautiful sense.
But from this it follows that if there is a maximal element, it's unique.
Yes.
Okay. And there is.
There is one in this. There is one in this family, and in this family there is no such maximal element. So.
Wait. So I'm sorry. I have to ask because you said so in this Borel set there is no maximal element. Do we know something about do we have like I don't know 2 maximal elements? Like the tree goes this way, or do we have?
Cannot, by definition. Because a maximal element means that you can reduce to it. So if both of them are maximal, you get the 2 directions.
I think he meant kind of a maximal subset that any other
Yeah, thank you.
an element of this subset.
Oh, maximal set. Okay. Well, the whole set.
No, listen to it.
I think what happens here is you have like and just increasing chains and
Okay,
no
thank you.
maximum.
Sorry.
Yeah.
I was just wondering, just out of curiosity. Thank you.
Okay. So moving on to dynamics. Okay. So a measure preserving system is a triple x mu t. X is x mu is a standard probability space, and t from x to x is measure preserving and invertible. And then we can again I will write MT for the set of I'm just going to do discovery any such system is isomorphic to 0, 1 lambda t prime, where lambda is the Berg measure. Okay, this is not
It's Lebesgue space
yeah.
in Rohling
Yeah.
terminology.
Here, by standard, do you assume that mu is non-atomic?
That's the assertion.
I agree. No, no, no.
Lebesgue and atoms.
Yeah. That's why.
Okay, so we can identify any measure preserving system which is non-atomic with a map, with a measurable map, measurable map from this measure space to itself, and there we have a topology given by well, there are several topologies available. For example, every T gives an operator of n on L2, and then on this L2 we have strong operator topology, and so we can well, pull back this topology and have a topology on the set of all measure preserving systems. So this can be again reasonably made into a Polish space, not just some abstract set. So I will just write MPT for the set of measure preserving transformations. So basically, people asked all those questions about well, measure preserving systems and this relation of isomorphism. And let me give you some results. So Hjorth he showed that this relation is strictly above E as infinity, and he also showed that this relation restricted to ergodic, only ergodic measure preserving transformations is not reducible to S infinity group action. And then Foreman and Rudolph Weiss they show that this is not Borel. Yes. And finally there is a conjecture of Marcin-Sawab is that this relation is bireducible, and this is what I didn't introduce, but what you said already. It means that it compares two ways with E Polish. So the conjecture is that
This maximizes the complexity.
yes, and yeah, it should be the way to see that it is actually a Polish group action is by looking at this representation. We can take all the measure preserving maps, measure preserving invertible maps of this unit integral, and this actually form a group. one is the conjugate of another by the ergodic group element.
But in this picture, I'm missing why aren't you discussing also the relation between MPT, general, and E-Polish? What do you expect there?
You mean without
Without ergodic.
Oh, ergodic, this is a subrelation of this. So
I know.
this automatically must be below
I
this
know,
one.
but do you conjecture that MPT is reducible with E-Polish?
Well, if this is reducible with E-Polish, then well, we know for sure that this is reducible. Well, we know that
Yes, okay, that's trivial.
this is also very easy because what does it mean? Well, what does it mean for two systems to be isomorphic? Well, two systems are isomorphic if and only if there exists some phi.
So I guess the question was: is there not a weaker version of the conjecture just for the MPT without the ergodicity? Is no one just everyone believes this conjecture is true and no one cares about the weaker version? Am I right? That would be the weaker conjecture.
Yes. You can do a weaker conjecture that.
That this is irreducible without the ergodicity.
Yes, and also this would be interesting.
Okay, so.
So anyway, I wanted to say that two systems are isomorphic if and only if we have this kind of relation, and this is just and here phi is invertible measure preserving. So this is okay. I'm explaining myself badly. Sorry, but this is a group action. This is a group of, let's say, M is the set of T 0, 1 to 0, 1 invertible measure preserving. Then the isomorphism relation is actually the relation of being of T and S being conjugate to each other in this group M.
And ergodic, you want phi being ergodic, right?
No, I mean phi is just n invertible measure.
Anyway, then you were at the bottom of the ergodic MPT.
Oh yeah. Then it's
Group is just
then it's the same group acting on a smaller set.
acting on something, not acting by more restricted isomorphism. So on what set of ergodic transformations?
Yes.
Okay, so it's not okay.
So this discussion, in principle, the group does not need to be related to the set in which acts, but here in particular examples, it actually coincide.
Yes. themselves to not just to ergodic systems which arise from C infinity isomorphisms of the tutorials, and they treated those as measure preserving systems, and again they got the same result, that it's not Borel. Yeah. So okay, and the same can be done in topological dynamics, because this was measurable systems. So
Can I have one more question? I'm
Yeah.
sorry for interrupting, but regarding those questions, if we restrict further, we can take, instead of ergodic, take, I don't know, mixing or some K-mixing or whatever you want. So is this also like kind of a question that is interesting? So instead of ergodicity, take some stronger property. So then the question may still stand. Is it still is it still not Borel, or is it, well, does it has any of those properties?
yes, I mean, it certainly is a valid question, and I think someone actually wrote some paper about K automorphisms,
Okay.
whether or maybe just ask the questions. But yes,
Okay, so it makes some sense. Okay, because I have very little feel for this topic, so I'm just asking. Is this still a valid question?
yeah. Obviously, okay, there are lots of classes that we can make up, and we wouldn't like to probably multiply those questions too much, but certainly you can ask about. I'm pretty sure someone asked about K automorphisms. So anyway, I want to discuss similar results in topological dynamics. So topological dynamical system. For me, it is well, xt. X is a compact Polish space. T is homeomorphism. As a Cantor system is one where X is homeomorphic to Cantor set, and system is minimal if it has no non-trivial subsystems. Oregon empty set and itself set. Okay.
It has no non-trivial compact.
Compact. Yeah,
Compact.
Closer.
No, closest no, because the original is Cantor, so it is compact.
Yeah.
So here we have well, more results. So topological derivation. So the relation of topological conjugacy for Cantor systems. Turns out it's bi-reducible. I should have a symbol for this.
I'm interested, what is this by from?
Okay.
By reducible.
So ER is reducible with E as infinity. This is a result of Gao and Camero. And then again, yeah, so a feature of this result and of this result is that when you look inside the proof, the systems are very well, they have a lot of invariant components. So people are kind of asked about what about the same for Cantor minimal systems. And there was a result of okay. I will write it like this, like Cantor minimal systems. So this is greater or equal than something called equality plus. The notation in this subject is very nice. And this is a result of a guy named Kaya. And this is not a okay. This was the best result at the time. And equality plus, I will only tell you that this is some relation which is both Borel and as infinity group action. And again, Gao, he also asked a question about this. Is it Borel? And again, he conjectured. Okay. Again, there is conjecture that this is reducible with E as infinity. So I think this is Gao stated it somewhere, and it is a result of me and co-authors that this is not Borel. So this is me, Felipe Garcia Ramos, Filip Kunde, Kosma Kasprzak, and Dominik Kwietniak.
Where is conjecture? Where is theorem? Conjecture is
Okay.
theorem is that it is not Borel, but above it is.
Conjecture is that
Conjecture still holds, but it's still not proven. You know, it's like in this direction.
It's not.
the theorem is weaker than the conjecture.
Why it is not?
But according to the drawing you drew in the beginning, the fact that we know that something is Borel or not Borel does not give us a clue if it is, for example, be reducible to S infinity.
No. Well, wait.
So why would you call
it is
this
Borel?
weaker?
If it is
I
Borel, then
know
it is not.
there is
reducible.
Borel and reduces to
One.
E
You
as
have
infinity.
of course it will be there.
And here you write that it's in
Where?
Borel. So
You see,
I'm lost in
it's not
definitions.
Borel, it's just saying to you that you are not on the left-hand side. But
Yeah. Okay, so
but I
this
don't
is a
see why,
very good
why
question.
you call it, I don't understand why you call it weaker, in other words,
Well,
according to the drawing.
okay, let me just repeat. There are three classes that we basically care about. One is the class of Borel equivalence relations, and this just means the relation is a Borel subset of x times x. Then we care about whether a relation is reducible to some S infinity group action, and
but
is it reducible to
no,
some.
it's not necessarily Borel.
Yes. You can. Some of the equivalence relations we talk about are not Borel.
Okay, but I thought they are Borel.
Okay, so
Okay.
the question is, if I understand any of this, so if we know that the relation is Borel, can it be still bireducible to E S infinity?
No, it cannot. Okay. The reason is simple. Is E S infinity is outside of Borel here, and okay, so E S infinity is not Borel.
Which is, I assume, proven just like similarly to the thing we did at the beginning, so with the tails and things like that.
Yes,
Because the E S infinity is somehow understandable relation.
It's some work, but it's proven. And then once, well, if you have, well, if let's say E is some relation, and well, let's say E as infinity is, let's say we have this situation. Well, let's say that F, well, the F is the reduction. Then F times F of E taken as a set equals E as infinity. So this is just well, the set of pairs. It's a set of pairs. We take that image through F, and we get exactly this. This is just checking the definition.
And this is not Borel.
And if this is if this was Borel, the map is Borel, then this would be Borel, but it's not the case. So it's just like this. Yeah. So this is what we managed to prove.
So this is Cracow. Like,
Yes.
Team Cracow.
That's right. Felipe Garcia Ramos is from Mexico. Philip Kunde is from Germany, but everyone is temporarily in Cracow. And
To clarify, so in this picture of various constellations, how bireducibility does allow to move from one piece to another in general?
No.
We have several pieces and they preserved by bireducibility.
The pieces preserve bireducibility. Like in this entire subject, we only care about equivalence relations up to bireducibility.
So this picture is more or less drawn for the equivalence class built with bireducibility.
Yes.
This is definitely like outside.
But reducibility can move
Up and down, left and right.
And kind of a
Hold on, down.
side result. Yeah.
No. Think about it, sorry.
And a side result of this theorem is that we show that flip conjugacy of Cantor minimal systems is also not Borel.
minimal Cantor systems, which would be reduction.
Yes, it would be sufficient, for example. Or, if someone would try to go in a from here to here, so you should take a countable graph. Out of this countable graph, you should somehow build a counter minimal system, and the construction should have the property that the two systems are isomorphic if and only if the two graphs were isomorphic. And if you do this in any reasonable way, the map will most likely be Borel. And then you would solve the conjecture. Okay, so I will just give you some words, a few words about the proof. Let me just once again write C for Cantor set. Homoeon of C is homeomorphisms. From C to C. And then minimal, let's say these are F such that CF is a minimal system. And we want to show that this relation is not a Borel subset of min C squared. So the plan is to take well, I will make it specific in a while. Take a subset of X, which is not, which is known to be not Borel. And build a Borel function f that goes from x to min C squared, such that f such that the pre-image of
Who is X here?
I will specify in a while.
I see.
It's some X is some Polish space and A is some set, and we will just try to do this. Because then again, by contraposition, if this is Borel, then this would be Borel, but it's not the case. So more specifically, we take well, it's really a kind of a standard each node it may have infinitely many children, and also in depth it goes.
Can you have 0 branches? Is that sometimes a problem?
Yes.
So the branches can stop. They can disappear.
Yes.
Okay.
So
really all trees. Everything may happen.
all trees with at most countably many children at any level. So formally, a tree is a set. Well, let me write large T for this again. Such that the nodes on the first level are labeled with numbers. The nodes on the second level are labeled by by pairs. So 1, 1, 1, 2, 1, 3, for example here, and so on, right? The children of this guy are named 1 to 1, and so on. And any node may have.
Just a note of, you consider actually rooted trees, right?
Yes.
Root,
I don't know, empty circles. So formally a tree is a subset of, is a set of sequences of various length over natural numbers such that if S is in T, then every prefix of S is also in T. So it's possible that maybe this node doesn't have any children, and then so trees, it's a subset of 2 to n to less than n, satisfying this property, and again it's a valid Polish space, and a tree is said to be ill-founded if it has infinite branch. So infinite branch means, well, I think it's several branch or just. And then it happens that the set ill-founded of ill-founded trees is not Borel. So we will use here in this strategy we will use A, the set of ill-founded trees, and X to be the set of all trees. So this means that out of a tree like that we need to build a pair of systems, and the construction should have the property that if the tree has infinite branch, then the systems turn out to be isomorphic, and if there is no infinite branch, then the systems turn out to be not isomorphic.
Infinite branches, it seems bigger than continuum. That's why it is not Borel.
Well, it should not be. It should not be continuum because
You take
set
you take subsets of continuum. It has bigger kernel. If you have such infinite branches. infinite branches.
But we have had countably many branches, countably many children. And there is that.
No.
I guess it's about that's assumed
2 to the n,
So
to
there's
the
a-
n
the indices form
is continuous.
segments.
This is but you take subsets of something.
No, it is a subset. Trees are a subset of this set. But it's a specific subset which
No.
is easily seen to be.
Because we fix on 3 and then we
Mm.
discuss it, not space of trees.
Yes. Okay, and okay, I have 5 minutes left, so I will just give you some very condensed summary. A subshift is a subsystem of well, this kind of system where again shift is just shifting sequences to the left. It turns out any Cantor system is an inverse limit of subshifts, and if we add minimal here, we also can add well, also any Cantor minimal system is an inverse limit of minimal subshifts.
Is it easy or necessary? Deep or
Sorry?
How difficult is it?
It's exercise.
Okay.
It's not very hard.
because
And then
clever.
under some additional assumptions, we have, well, if we have an infinite, well, we have some, we are taking some inverse limit. So let's say these are pi n, and we have some other chain yn. And we have some maps. Some maps fn plus 1 fn. Then we have equivalent condition. One is, well, let's say we take 2 inverse limits. Let's call this rho n. And well, the second condition is there exists fn from xn to yn in the automorphism groups of such X, and then stuff like that. That's it for this stuff. Thank you.
Thank you, Captain.
Are there any questions? Maybe I can ask the question. So in this, what you described, you were considering Z actions, right? Because
Yes.
what happens if you try to consider, let's say, Z2 actions on Cantor sets and so on? Is it like sensitive to this, or it has it's not significant?
I never tried this. There were some papers about studying these complexities for subshifts. So well, there are maybe like 5 papers about applying this theory of Borel reducibility to various classes of subshifts. And there, someone, I think there is a paper of Sabok and Salkov where they consider subshifts over arbitrary group, not just Z. And there is also a book of Gao and some co-authors where they also consider subshifts over not just Z but arbitrary group G. And my feeling is that it shouldn't really be, it shouldn't change the final answer, because we already expect that with Cantor minimal systems it's going to be reducible with this E as infinity. And with other group, I would guess it's also E as infinity.
But about non-amenable group, would it make a difference?
I'm
Typically,
really,
yes.
I'm not really knowledgeable about this stuff.
I mean, if you take Homeos C as the group, this thing is brittle. So there is some limit where you can push it. But now you said about the conjecture, but what about your result?
No, our result is only for Z, and yeah, I don't know what would happen with.
Okay. Are there any questions online?
Participants online are encouraged to ask questions.
Now or forever keep silent.
Exactly.
Or is this for 2 minutes?
It seems they choose to remain silent.
What?
They choose to remain silent.
They chose to remain silent. Okay, so if no other questions,